Hello students, in this video we will study another application for the electromagnetic induction phenomenon, which is the DC electric motor. Basically, this DC electric motor is found in almost all the electric appliances that have some rotation in them, okay? Now we're gonna understand how this DC electric motor works, the principle of function, what is made up from, and we're going to see how electromagnetic induction works with this device. So, first, we have a coil, okay, which is basically any conductor that's made in the shape of a loop. And this coil is connected to an electric supply, an electric power supply, a generator. And the current from the supply is traversed to this coil via this commutator here, okay? So we have an electric current moving from the generator to the coil into this blue wire up and then down into this green wire and then back to the negative of the generator, okay? And this coil is placed in a uniform magnetic field, B. This magnetic field is created by placing the north pole of a magnet and the south pole of the magnet in this way and placing the coil between them. Now we know that from Laplace's force, when we have an electric current traversing a conductor and this conductor is placed in a magnetic field B, this conductor is subjected to a force F called Laplace's force. It's the electromagnetic force. Okay, this force, we can know its direction using the right-hand rule. Now let's study the direction of the magnetic force into this like blue wire. So here, this is the right-hand rule. If B is going into, if it's oriented to this direction, and the current I is going upwards, we know that the force F would be inward, and we represent it by this X here, meaning that it's going into the screen. Okay, so if I is like this, upward, and B is horizontally to the right, then F would be inside. Okay, let me draw it in a better way, like this. Okay, so this means that it's going into the screen, inside. Let's draw it here. Let's use this nice purple color. So the force F would be oriented inwardly, okay? And let me make it thicker. And we call it F1, okay? Now let's study the green part. We have the current I moving downwards and the magnetic field B also horizontally to the right. Let's see the right hand rule for that. We have, this is our right hand, okay? And we have I downward and B to the right. Then F would be something like this, okay? Or like, by this I mean it's going inside, okay? Not inside, actually, it's going outside of the screen. So again, I is downward, B to the right. This is going outside the screen, so outside the screen. And we represent it by a dot, meaning that it's going just outside the screen. If you want to draw it here with the nice purple color again, it's gonna be something like this. F2. Okay? Observe now this coil and the force is acting on the two sides of the coil. One force is pushing one side inside and the other force is pushing the other side outside. F1 and F2 form a couple of forces, okay? And this couple of forces, it has the same, like both of them contribute to the torque of this coil, and they will cause the coil to rotate. So in like this, okay, the coil will rotate like this, so it will have an angular speed in this orientation. Again, imagine it with me. If this one here is pushing inward and this one here is pushing outwardly, then the coil will be rotating like this, okay? So you can see now how placing a coil which is traversed by an electric field, and I'm sorry, it's traversed by an electric current and is placed between two magnets and is placed in a uniform magnetic field, will cause this coil to rotate. With this, we are changing electric current into a mechanical, we're changing electric energy into mechanical energy, right? But we know that as this coil rotates, the angle between B and the normal is going to be something like this. The normal is going to change. Now, as the angle changes, it means that the flux is changing, and thus we have an electromotive force, an E, which is induced, right? Let us just review what we have already. So, this is a coil here. This coil is supplied with an electric current from the generator. This current moves through the coil. Because this current moves through the conductor, and this conductor is placed in a magnetic field, the coil is subjected to Laplace's force, and we know Laplace's force, the direction of the force, using the right-hand rule. So the blue coil, the blue part of the coil, is subjected to a force inwardly, and the green part is subjected to a force outwardly. These F1 and F2 form a couple of forces. This couple moves the coil in this direction. It makes it rotate, and this rotation causes a change in the magnetic field B. It causes a change in the magnetic flux caused by the change of the angle between B and the normal. And this change in B will lead to an induced electromotive force. Okay, let's go down here. Now, so as the coil rotates, the magnetic flux across the loop changes, and this means that an electromotive force is induced. But according to Lenz's law, this electromotive force is going to be created opposite to what creates this electromotive force. And we see that if the potential difference of this generator is oriented from the positive to the negative, something like this, right? And the current is moving like this, then the electromotive force induced would be opposite to the one that is like from this generator here, right? If the current I was moving like this, the induced I should be in this direction. That's according to Lenz's law. And because of that, we call it back electromotive force, because it opposes the EMF of the generator. The generator, the one that supplies us with the electric energy, it has its own electromotive force. And there is another electromotive force, which is the induced one that's created by the coil as it rotates, and the magnetic flux changes as it rotates. So this induced electromotive force is called back electromotive force, and it's opposite to the one in the generator. So if the one from generator is like this, the back electromotive force would be in this direction. Okay, now let's do some formulas. This is the magnetic flux, it's Bs cosine theta. We're just gonna take the coil with n equal to 1. It has one turn, okay? and theta would be omega t plus theta 0. We know that from the previous video. And the electromotive force according to Faraday's law is minus d phi over dt, and we know it would be bs omega sine omega t plus theta 0. And the maximum value of this electromotive force would be, if this was 1, so it would be bs omega. Okay? Now we're going to orient the positive direction along I. So let's take the positive direction in this way. So this is the positive direction. It's along I. If we took the positive direction along I, and we know that this coil here, it has a resistance R. The coil has n turns. We took n equal to 1, and it has a resistance R. Okay? We have a generator connected to a coil that has a resistance R. We know that according to Ohm's law, so let me write it up here. So according to Ohm's law, U of the coil, or UCD, did I put C and D or no? No, I didn't. Let this be C and let this be D. So UCD would be equal to R multiplied by I, right? It should be equal to the current I multiplied by the resistance of this coil. But we have an induced electromotive force, or a back electromotive force, created by this coil. So what happens is that the potential difference of this generator equal to the resistance of this coil multiplied by I minus the back electromotive force. Okay? So UCD would be Ri minus E, which is the back electromotive force. And for this motor to function normally, we need to have E smaller than, E smaller than Ri, so E should be basically smaller than just U by itself. Okay? And in the end, let's say if we have a generator that is generating, let's say 12 volts, okay, and the electromotive force, back electromotive force is 2, then UCD would be equal to 12 minus 2, it would be equal to 10 volt. Okay, that's basically how it works. And this value here should always be like less than 12, if 12 was our potential difference of the generator without the electromotive force, the back electromotive force. Basically, that's how an electric motor works. It uses the principle of having an electric current passing through a conductor through a magnetic field. It will create a force F, and with another force F1 and F2 on the two sides of the coil. This couple of forces will cause the coil to rotate, and then this rotation will cause a change in the magnetic flux, and this flux will cause a back electromotive force, and this back electromotive force opposes the direction of the electromotive force of the generator, and then the U, the potential difference between C and D, would be R times I. R is the resistance of the coil, and minus E, which is the back electromotive force. And that's it for today.